All right, let's talk about this. So the first question, interpret r squared in context. What do we call r squared? What's it sometimes referred to as? The coefficient of determination. The coefficient of determination. And what does it tell us? Yes, it tells us the variation. It tells us how much of the variation in y, how much of the differences in the y values is because the x is different. So how would you interpret, let's see, what is r squared? Let's start there. 0.943. So if I'm going to interpret r squared, what do I want to do to that 0.943 first? Put it into a percent form. So what would it be as a percent? 94.3%. All right, so 94.3%, what? That is perfect. That is absolutely perfect. 94.3% of the variation in stock price can be explained by the linear relationship with X, or with years after 2000. That is 100% correct. Love it. Love it, love it, love it. All right, number 2 says to write out the equation for the regression line. Be sure to include context for the variables. So they did a lot of the legwork for you already on this, right? You were given the summary statistics back here, and you had an equation right here, but we needed to write this in context. So instead of writing y hat, what are we going to put in the place of y? Stock price goes in the place of y. In the place of x, what would we have? Years after 2000. Years after 2000 takes the place of x. So number 2 should look like this. Stock price hat, because we are predicting the stock price with this model. We are not finding the actual stock price. Stock price hat equals negative 20.5958 plus 2.7938, and then in parentheses, years after 2000. Use the linear model to predict the stock price for 2014. Show your work. So what are we putting in for X? 14. What did you guys get for this one? 18.5174. We're talking about money though, so what should we round to? 18.52. Love it. Find the residual for your stock price prediction for 2014. A residual is calculated how? Actual minus predicted. What was the actual stock price for 2014? 13.39. So we have 13.39 minus 18.52, which gives us a residual of negative 5.13. So the actual stock price was $5.13 less than what the model predicted the stock price would be. All right. Before we go look at number 5, I want to come back to these summary statistics here, and I want to look at r squared. What would the r value be? If r squared is 0.943, how do we calculate r? Yep, we do the square root, 0.943. 0.971. Positive or negative? Why is it positive? You guys are right. It is a positive r value. Looking at the graph, or even at the equation, how do we know that it's a positive r value? Yes, it's a positive relationship. We have a positive slope. If you have a negative slope, when you do the square root, the calculator is never going to spit out a negative number. When you do a square root, the calculator is always going to spit out a positive number. You have to look at the graph or the equation or both to determine whether r is going to be a positive or a negative value, because you will have to put the negative sign on there if it's a negative. Calculator won't tell you that. All right, let's go down and look at number 5 now. That's a pretty strong r, 0.971, right? Number 5 says, explain why the residual plot indicates that a linear model is not appropriate for this data. There's a U pattern. Yep. The residual plot has a clear curved pattern. You could say it has a U shape, or it goes positive, negative, positive. You could say it has a curved pattern to it. We want to indicate that that curved pattern, that U shape, is unacceptable for a linear model being the best model. That doesn't mean a linear model is a horrible model, but it means it's not the best model. R being 0.971 by itself is not enough to determine linearity. You got to look at the residual plot. If they don't give you a residual plot, there's still a little bit of a way that you can tell from the scatter plot. The residual plot we're looking at, is it above or below the line of best fit, right? So if I go back and I look at my original graph, I'll bring it right back to here in a second. If I look at my original graph, these 2 points are above the line of best fit. The next 3 points, 4 points, 5 points are below the line of best fit. And then we have 2 points that are above the line of best fit again. If I don't have the line of best fit on there, it's going to be hard for me to tell. But with the line of best fit, I can kind of see how the residual plot is going to go. If you don't have the line of best fit on your scatter plot, and all you have is a scatter plot and summary statistics, you have to do the best you can with what you have. When you have the residual plot, you want to look at that for linearity. All right, let's flip the page. We've just decided that a linear model is not the best model for this data. So we are going to transform the data to make it more linear. We are going to transform the data to make it more linear. We will do this by taking the log of the stock prices. Now, when I say we're going to take the log of the stock prices, if it's just log, what's the base? 10. This is a base 10. And so we're going to use the log button. We're not going to do ln, we're not going to do natural log, although you could, but we're not going to today. We're going to just do regular base 10 log of the stock price. So they've gone through and done that for a bunch of these different stock prices. They did log of 2.75 and they got 0.4386. On your calculator, I want you to do the log of 2.64. 0.421. Yes. Let's take it out to 4 places since they took theirs out to 4 places. We get 0.4216. If you need help finding the log button on the graphing calculators, I'm happy to help you find the log button. It took me a minute because I'm slow. Take it out to the 4th place, yeah. And I'm only taking it out to the 4th place because that's the way they did all the other decimals on here. They took theirs out to the 4th place. All right, so I'm going to add that point to this scatter plot. Years after 2000 is 8. And the log of the stock price is 0.4216. So if this is 0.4, I don't know, 0.4216 is going to be about here-ish, something like that. Let's do the same thing for 2014. For 14 years after 2000, we have a stock price of 13.39. What is the log of 13.39? 1.1267. So then we're going to come over to 14 years. We do 1.1267, so about here-ish. We've got the equation right here for this scatter plot. But just like your graphing calculator wouldn't know that we've taken the log of all the y values, that's exactly what we've done. So this y hat here is actually, I don't want to go through my point. Log of the stock price is my y hat. Log of the stock price is my y hat. Years after 2000 is still my x. I would like for you guys to do 7 and 8 now. Do 7 and 8 and then pause. I want you to interpret r squared in context, this new r squared. And I want you to write out the equation for the regression line in context. Give us about 2 minutes to do those two problems. All right. How would you interpret r squared in context this time? That is perfect. 95.3% of the variation in log stock price. Because now our y is different. Now y is the log of the stock price. Can be explained by the linear relationship with x equals years after 2000, or you can just say years after 2000. Write out the equation for the regression line. Be sure to include context for the variables. So that should look like this. Log stock price hat equals negative 0.1533 plus 0.0871 and then years after 2000. If you have not already, and I don't expect you to because I didn't tell you to, I want you guys to try to do number 9. Use that linear model, the log stock price model. It's still a linear model because we have a y-intercept and a slope. I want you to use that to predict the stock price for 2014, just like we did on the front side, but new equation. And we want to solve this for stock price, not log stock price. I want the stock price at the end. Question. That's right so far. But now what are you going to do with that number? Because we're using the transformed data. Yep, we're using this. This is a better model, so this is what we're going to use now for predictions. All right. What's the first thing you would need to do on this problem? Plug in 14 in the place of? Years after 2000. Exactly right. Woo! Went to a different screen. There we go. So we're going to plug in 14. When you put the right-hand side of the equal sign into your calculator, what does it give you? 1.0661. Perfect. Now, let's see who remembers what to do with this. I have log of my y variable equals this. What can I do with that? Because I want to get just stock price by itself. I don't want it to have the log next to it. Close.
What's the word? Exponential.
Yes, we're going to exponentiate. Or you could just rewrite it as an exponential. You can either exponentiate, where you raise both sides to the power of whatever this is. So put 10 to the power of this, 10 to the power of this. Or you can just rewrite this as an exponential, where this 1.0661 is your exponent. So we're going to take the base of, what did we say the base on log was? 10. So 10 to the power of 1.0661 equals stock price. I'll get that thing off the screen here in just a second. Sorry about that. Please. Let me get this off the screen. So 10 to the power of 1.0661 equals stock price hat. Why is it so important that the hat is on top of stock price still? Means it's a prediction. If I leave the hat off, I'm saying that is the actual stock price that was recorded in that year. That is not the case. Yes.
So if we leave off the hat, we lose points.
Yes. Yes. If you leave off the hat, you're saying what you're reporting back was actual collected data versus this is what my model predicted the data would be. All right, so what do we get? 11.6439 or 1164 if we're taking it out to the nearest penny. 1164 is equal to stock price hat. Little review lesson on what to do with logs. Right. All right, let's look at this residual plot. What strikes you as the biggest difference between this residual plot and the one on the other side, the one on page 15? There's no concrete curved pattern. Like, don't get me wrong, I can draw a shape through there. I can play connect the dots with anything. But what we're looking for, the big no-nos, are shapes like this, or ones that go like this. That's what I don't want to see. If it goes up, down, up, like that's good. That is more random than what we had before. What we had was a much stronger pattern. This is much less of a pattern. So what does the residual plot indicate about about this linear model for the transformed data? Better or worse? Better. There's no clear pattern, so the linear model is appropriate. On page 15, we made a linear model using X as years after 2000 and Y as just the stock price. On this page, page 16, we made a linear model where X was still years after 2000, but Y was log stock price. Which model will give us better predictions? The one on page 15 that we came up with first, or this one? This one. So page 16 is going to give us a better model. It says give 2 reasons. We want to give at least 2 reasons. What's one possible reason? No clear pattern on the residual plot. The residual plot has less pattern and more randomness. Yes. Stronger R value. The R value is closer to 1. It's 0.976. Or sorry, it was 0.976. Now it's 0.976. It was 0.971. Good grief. Let me get myself straight here. It is now 0.976. It used to be 0.971. So we have an R value that's even closer to 1. That is a stronger linear pattern. And I could add another reason and say my R squared is even closer to 1. As R squared strengthens, R strengthens. There you are. I'm going to have you at that table over there. Right. We can flip this over to page 17 now. Do I need to go back?
Yeah, just for a second.
Okay, no worries. All right. All right. You good, Jordan? Okay. Going over onto page 17, transformations. We have linear, we have exponential, we have power. There's also quadratic. To make predictions, you're going to plug in x and solve for y. So if it is a log y equals a plus bx, you're going to exponentiate both sides, or you would rewrite as an exponential function. If you do ln instead of log, it would be e to the power of. If you have a quadratic model, y squared equals a plus bx, then you would need to square root both sides to get y by itself to make a prediction. That would be for a quadratic model. Let's check out the check your understanding. It says a bulk candy supply store offers chocolate truffles in several cube-shaped boxes. The number of truffles in each box varies based on the side length of the box. Here's a scatter plot showing the number of truffles that can fit in boxes of various side lengths. Because length is one-dimensional and number of truffles to fill the box, volume, is three-dimensional, a power model of the form number of truffles equals k times side length of box cubed should describe the relationship. Here's a scatter plot with x equals side length of box cubed and y equals number of truffles, and then the computer output is down below. So let me back up just a second. This graph right here is just the side length of the box in inches and number of truffles over here on the y-axis. What do you notice about this graph? It's curved. I know when I do a residual plot for this, it's going to have a U shape because my data has a U shape to it. So when they corrected that and they had x equals side length of box cubed, so now x is side length of box cubed, this is the plot that came back. Do you see that it got straighter? It's much less cubed. Here's the regression output. I want you to give the equation of the least squares regression line, making sure that you're doing this in context. Any variables should be words. And then suppose you want to fill a box with a side length of 5 inches. Use your model from number 1 to predict the number of truffles that this box could hold. I'm going to give us about 3-4 minutes to do this.
Does it become a part of the equation?
So side length of box cubed and then parentheses.
Okay, so therefore that's the variable. The cubed is a part of the
Side length of the box cubed. Or you could put it outside the parentheses technically, but yes, that'd be to the 3rd power right there. Yep.
And then it's not a part of the equation, right?
The cubed is, if you're using it to make a prediction.
Okay.
Because here they're just telling you the side length of the box. To use this model, you're going to have to do that to it.
Okay.
All right. So what does my equation start with? Number of truffles hat. Yes. So we're going to have number of truffles hat equals what? 0.095 plus 2.2 parentheses side length of box cubed or side length cubed. Perfect. Suppose you want to fill a box with a side length of 5 inches. Use the model from number 1 to predict the number of truffles that this box could hold. So what's the first thing that's going to happen to 5? It's going to get cubed. So it becomes what? 125. And then we have that 125 times 2.2 plus 0.095. And what do we get? Yep. I said 275.1. Since it's a prediction, I can have decimal values. My prediction can have decimal values. The actual value would not have parts of truffles, but a prediction from a model can have decimals. We're going to tend to see the same thing with anything else. Like, if it makes sense to round it, if you said about 275 truffles, I would absolutely accept that, because 275.1 is about 275. So if you round it to the unit that makes the most sense, as long as you use a word that indicates that you rounded it, that would be perfectly fine. So don't say exactly 275, but you could say about 275 and you'd be fine there. Do you guys have any questions for me about this? All right, we are going to practice this on Monday some more, looking at different models and transforming this data. Homework's due on Tuesday. Monday is the last lesson of this chapter. A week from today is your test. A week from today is the test. Monday will be our last lesson. Homework's due on Tuesday. The homework mostly focuses on transforming data. So now that we've had a lesson over transforming data, you can start on some of that. There's still some pieces that you might not be able to do. This homework is shorter than the last homework. It's still a front back, but it is shorter than the last homework.
It's less than 2 questions.
It is not, I don't think it's less than 2 questions, but it doesn't have G parts to the questions either. There is a reading assignment, 13 pages, page 213 to 226. Page 213 to 226. On Tuesday, the day that your homework is due, you will get the test review for this test. Wednesday, we will practice with some FRQs. Tuesday, we'll do some multiple choice practice. Wednesday, we'll practice with FRQs. Thursday, I'll take questions over the test review that you guys will have had several days to work on. And then Friday will be your test over scatter plots and 2 variable quantitative data. Do you guys have any questions for me on this lovely Friday? All right.